Find exact phrases fast with a positional inverted index. By the end, you will have a tiny Python baseline that maps token positions, answers exact phrase queries, supports a one-word slop, and extends to multi-word phrases. You will see why positions matter, how adjacency is tested, and how a single slop parameter widens or tightens matches. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Phrase search solves a practical need. Users often want exact snippets like a product name or a quoted sentence. A positional inverted index stores where every word occurs, so you can test order and adjacency without rescanning documents. Compared to dense vector search, this method gives exact, deterministic phrase matches and is cheap on CPU for moderate data sizes. The trade-off is it will not capture paraphrases or deeper semantic similarity. Use it when literal phrasing matters, like legal text, logs, or code search. The intuitive idea is simple. Instead of just listing which documents contain a word, record the positions inside each document. For a two-word phrase, you intersect documents, then check if the positions line up next to each other. For longer phrases, you chain those adjacency checks. That position information is what makes phrases precise and fast to verify. We will build a minimal pipeline and run sample phrase queries on a small corpus, so you can see hits and gaps in real time. Now we will map tokens to positions inside a single document. This snippet builds a positional map for the first document in a tiny corpus. The variable docs holds two small texts on separate lines. The variable toke splits the first document into words so we can walk the text and record positions. The dictionary pos collects positions using set default, so each word accumulates a list of indices as we iterate. Finally, we look up the word quick in pos and print the list of integer positions where it appears inside that first document. This quick check confirms our per-word position mapping and gives you confidence that indexing positions works at the single document level. Next, we will expand mapping across all documents into a full positional inverted index. This example builds a proper inverted index that maps every term to a nested mapping of document ID to position list. We enumerate docs starting at 1, so our document IDs are human-friendly. For every token, we use set default twice, once to ensure the term has an entry and once to ensure the document ID maps to a list we append positions to. After indexing, printing a sorted view for the term quick shows which documents contain it and the exact positions inside each document. That output verifies the index spans multiple documents and gives you stable, readable output to use for phrase queries later. Now we will test exact adjacency for a two-term phrase. This code finds documents where the exact phrase quick fox occurs as adjacent tokens. The tuple Q holds the two-term query, and the variables A and B fetch postings for quick and fox from the positional index IDX. We first compute the intersection of their document ID sets to get candidate documents. Then for each candidate, we check if any position P in quick is immediately followed by P+1 in the fox position list. Matches are collected as hits and printed as document IDs. The result demonstrates how storing positions lets us confirm true adjacency without rescanning the raw text. Next, we will allow a small flexible gap between terms by adding slop. This snippet introduces a slop parameter that tolerates a one-word gap between quick and fox. The variable slop controls how many intervening tokens we accept. So increasing slop admits looser matches and may boost recall while lowering precision. We again intersect candidate documents and then compare every quick position P with every fox position Q, accepting pairs where the distance is within slop +1 steps. You can tune slop to balance strict phrasing against natural variations. The printed IDs show matches beyond strict adjacency, and illustrate how Slop retrieves near phrases that still read naturally. Finally, we will resolve a longer phrase across 3 terms by chaining positions. This example resolves a 3-term phrase "quick brown fox" by testing for a consecutive chain across the positional index. The list Q holds the ordered terms "quick brown fox." For each candidate document that contains the first term, we test whether any starting position P is followed by P+1 for the second term and P+2 for the third term. We fetch positions from IDX and use all and any checks to confirm the full consecutive chain. This method extends exact phrase logic to longer queries without rescanning the original text and prints document IDs where the full phrase appears in order. Recap: what we built, when to use it, and one caveat. It is a positional inverted index that records term locations to support exact and near phrase matching. Use it when literal order and adjacency matter, such as quotes, code, or legal clauses. One caveat is it matches literal phrasing only and will not find paraphrases or semantic equivalents. Next step, scale this same pipeline to a larger corpus and add a simple evaluation step, measuring query latency and precision as you increase the Slop value and corpus size. If practical search tools interest you, subscribe and watch the rest of the IR series for hands-on tutorials and benchmarks.